Hey, good afternoon. Welcome. So thanks for coming in person. All the rest of the seminars except one, I think, will be in person. So it's great to see you all here. And before we begin, I'd like to thank the Atkinson Center and the Biological and Environmental Engineering Department for their support of this seminar series. So today I'm really pleased to welcome Angie Pendergrass, Professor Angie Pendergrass. She joined Earth and Atmospheric Science Department in 2020, right? Mm-hmm. So she came during the COVID semester from Boulder, Colorado. Boulder, she took a number of jobs, including postdoc at Advanced Studies program at NCAR. Before that, she graduated from the University of Washington in meteorology. Even before that, she obtained her Bachelor of Science from Miami University, combining her interests in meteorology, climate, math, and physics. So I propose that we give this seminar on a rainy day, because Angie's going to talk about Earth's water cycle and the change in climate. And she specializes, in fact, in extreme precipitation and its response to climate variability and change. And she recently won the 2022 Outstanding Early Career Award with the American Meteorological Society for her fundamental contributions to understanding extreme precipitation and its role in the climate system. So let's welcome Angie, and thank you for coming in.
Thanks for having me, and thanks for giving me this opportunity to tell you about the water cycle. I'm going to try to give you a really big picture view of what it is I'm looking at and kind of why. And I like to start from this view here. So this is an image taken from NASA's Discover satellite. So this is a satellite that's sitting in between the Earth and the sun. It looks back at Earth and gives us these images of the full disk of Earth. This one is from 2015, but this is one of the important perspectives that turned out to be important for precipitation that I'm going to tell you about today. Okay, so when I say water cycle, what I mean is that I can click slide almost. There we go. So when we're talking about Earth's water cycle, we are talking about the trajectory that water molecules take through the climate system. So we can go around this cycle and we can start anywhere and end anywhere. But if we start with liquid water in the ocean, in lakes, it evaporates, becomes water vapor, condenses again, releases latent heat into the atmosphere before falling back to Earth as precipitation. When it falls on land, then it runs back off to the ocean as runoff. So throughout this cycle, the water molecules it's transferring not just the mass of water around the climate system, but it's also taking energy with it. So a lot of my work is at this intersection of thinking about the mass and energy transfers that water takes through the climate system. There are a lot of scales that are important for this problem. And so to try and think about that, I have this schematic diagram for you. So we know that when rain falls, we are thinking about what's happening at the scale of individual water droplets, the scale of water vapor molecules attaching themselves to aerosols. But those water droplets are also coming together and interacting with each other. A bunch of them, that's a cloud. So we go from the scale of water droplets, which is millimeters at most, perhaps even less, up to the scale of clouds, which is more like perhaps a kilometer. Now, these clouds also have a longer time scale. The scale over which they evolve is more like hours instead of perhaps minutes that an individual water droplet would take to fall from a cloud to the earth as precipitation. Okay, so we've already crossed a few orders of magnitudes of scales in space and time when we're worried about precipitation. Now, clouds organize together and form various types of weather systems. And those have scales ranging from regions of the country to the scale of the continent. So we also have to worry about how those cloud systems are kind of moving around and forming and dissipating on the scales of thousands of kilometers. Now, those phenomena are organized by weather systems that are growing and dying on the scale of hemispheres, right? Getting close to the scale of the planet. So tens of thousands of kilometers. What I already alluded to at the beginning of the talk is the scale of the planet itself. And we'll come back to that in just a minute, thinking about how precipitation interacts with the forcings of global warming. And then finally, we have to worry about scales of the whole solar system in the universe, right? One of the factors that affects precipitation is actually the variations in energy coming from the sun. So we have to worry about variations in water and energy from scales of millimeters or even micrometers up through millions of kilometers. And also on time scales from just a few minutes all the way to thousands of years in order to understand precipitation and all of its variations. Okay, so the point of my telling you this is there are many ways that you can come at precipitation, and people think about things from all kinds of different scales. So I started out my work thinking about what happens on this global scale, and over time I've kind of come down in scale, thinking about the global warming forcing and how that connects to extreme precipitation events that are happening on these smaller scales. Another thing that's common in the field is for people to start at these smaller scales, say thinking about what happens in Ithaca, New York, what happens to precipitation here, and what's happened over the last few decades, and then trying to connect that back up to these other scales. So there are lots of different ways to look at this problem. So since I hear that you've already learned a bit about the climate sensitivity and radiative forcing in previous seminars this semester, I thought that would be a good place to start to connect this global warming forcing to precipitation and how it changes. Okay, so coming back to this global scale, when we are thinking about the temperature of the planet, what that fundamentally comes down to is the energy flowing into the Earth system and out of the Earth system back to space. These exchanges between space and Earth. So the energy that comes in from the sun, 2/3 of it are absorbed and 1/3 is reflected. That is in balance with energy that's emitted by the Earth in longer wavelengths. And if we let that run for long enough without changing anything too much in terms of forcing, we'll get to an equilibrium where the absorbed sunlight by the planet is equal to the energy that's emitted by the planet. And that happens at some temperature. And that's kind of our baseline. The climate starts out. Okay, so now coming back to this energy that's emitted by the Earth, when we change greenhouse gases, we increase the amount of greenhouse gases, we decrease on a very short time scale, we decrease the amount of energy that's emitted by the Earth when we change the emissivity of the atmosphere. Now, when we do that, we haven't changed anything about the absorbed sunlight yet. So the absorbed sunlight becomes greater than the energy emitted by Earth, because we decrease the amount of energy emitted by Earth. So that moves us away from our equilibrium, and warming ensues. Heat accumulates, temperature increases. The increase in temperature increases that energy that's emitted by the Earth again. So we can find a new balance at a higher temperature. Why this is red. Find a new balance. Okay, so that's what's going on to regulate Earth's temperature in the face of greenhouse gas changes. But what does that mean for precipitation? So if we want to understand what that means for precipitation, we have to go back to the beginning. Think about these exchanges between space and Earth. But instead of looking at the Earth as a whole, we have to focus on the surface and the atmosphere. So these exchanges of energy between the surface and atmosphere. Kind of important if we want to understand precipitation. So to zoom in, if we think about these layers of space, the atmosphere, and the surface, it's pretty idealized. Like I mentioned at the beginning of the talk, we start from this point of evaporation. We have water vapor molecules that evaporate from the surface into the atmosphere. And when they do that, they require some energy to move from the liquid to the gaseous state. And so that actually comes from the surface and it cools the surface. Now, these water vapor molecules eventually, after moving around, potentially condense again, form water droplets, they form clouds, they release their latent heat. And then that water, the mass, falls back to Earth as precipitation. So as the water molecules take this cycle through the Earth system, they actually transfer energy from the surface to the atmosphere. So that energy, if we're in equilibrium, has to be in balance with all the other components of energy being exchanged between the atmosphere and space, and the atmosphere and Earth's surface. So that includes the sunlight that's absorbed, like we were worried about before, and the energy that's emitted from the Earth system back to space. But now we also have to worry about these other components. Some of the sunlight is absorbed at Earth's surface, and some of it is absorbed in the atmosphere. Some long wave energy, this energy that's emitted by Earth, comes from the surface and then is absorbed within the atmosphere. Some escapes to space. And then the atmosphere itself emits some more long wave energy from the atmosphere back to the surface. Now, evaporation is a transfer of water molecules from the surface to the atmosphere. We also have to worry about sensible heat. So that's direct transfer of heat from the surface to the air that's in contact with it, which is then transferred around through motions of the air. Okay, so all of these components add up to balance each other in equilibrium. Now, when we add greenhouse gases or other global warming forcings, we alter these balances, not just at the top of the atmosphere, but also these balances between the atmosphere and the surface. So we can change the amount of solar energy that's making it to the surface. When we increase the temperature and the emissivity of the atmosphere, we change these exchanges of long wave energy between the atmosphere and the surface. And because of some changes in the state of the atmosphere, we end up having less sensible heat flux. And then to balance all of this, we end up with more precipitation on average in the global mean in response to global warming. Okay, so that's the kind of big cartoon picture of how global mean precipitation responds to the global warming forcing. And hopefully you get a little bit of an idea of how that connects to the changes in temperature with warming. The bottom line is that what global warming means for average precipitation is that the same effects of greenhouse gases that lead to warming also lead to more precipitation on average. Okay, now coming back to our schematic here of the different scales over which we have to worry about aspects of precipitation, right? We're just focused on this scale. But we know, living here in Ithaca, that we don't actually care too much about what happens in the global mean. We kind of care about what's happening here in Ithaca. And we also care about how that's varying over time from hour to hour and day to day and year to year. Okay, so if we move away from the global theme and start thinking about how precipitation varies in space, this is kind of the first place I want to start. Now, this is a map that's taken from an observational data set. So it's just the average precipitation over a fairly long time everywhere on the globe. And so there are a lot of different features you can see here. You can see there is this region of very high average precipitation over the tropical belt. You can see that on average in the Pacific is a little bit north of the equator. There's this extension here that comes from northwest to southeast from the equator across the Pacific. That's the South Pacific Convergence zone. We can see something that's a little bit parallel to that over the South Atlantic. And then looking at the Northern Hemisphere, we can also see similar features here. And so these are the storm tracks. And they come from southwest to northeast across each ocean basin. When we get to the continent, so here in the US, we're in the mid-latitudes, and we can see that we've got this region of less average precipitation in the southwestern US. As we go toward the northeast, it gets higher. This region of less average precipitation over the southwestern US is contiguous with this region of very little average precipitation over the northeast Pacific Ocean. We can see features like that also in the southeast Pacific, in the southeast Atlantic, and in the northeast Atlantic, and also in the South Indian Ocean. Okay. What else shall we look at here? If we go down to the high latitudes of the southern hemisphere, we've got this region of high precipitation on average that circles this latitude where there's no land. And going up to the northern high latitudes, we've got quite a bit more complex mean precipitation pattern, and that's associated with the mountain ranges that we have in the northern hemisphere that kind of disrupt the average flow that we have in the southern hemisphere. Okay, so that's the really big picture of precipitation on average. If we zoom in a little bit more to that continental scale, think about what happens in the US. We can see more of this gradient from southwest to northeast, and we start to see even more variations at smaller scales. So I did my bachelor's degree at the University of Miami in Florida. There's quite a lot of precipitation on average in South Florida and really all along the southeastern part of the US. You can see that where I did my PhD up in the northwestern US, there's also a local maximum of precipitation. And it's also got something to do with those mountain ranges that we have in the West. You can see a number of variations across the mountains in other parts of the US and really lots of things going on here. Okay, so these are still averages over time. And next, what I want to show you is a satellite image of precipitation that is taken from, let's see, there we go. This is a satellite image taken from a constellation of satellites of precipitation over the last week. So here you can see that if we look at precipitation systems as they evolve, they're much more complex than we see in that map of average precipitation. Now we can see the movement of these systems in the mid-latitudes of both hemispheres from west to east. You can see these long systems of precipitation, these fronts, both in the southern hemisphere, mid-latitudes and high latitudes, where right now it's fall, and also in the northern hemisphere, mid and high latitudes, just like we can see today's the 7th. So we can see this system that is causing the precipitation outside. If we look at the tail end of this, we can also see that there are very different systems leading to precipitation in other parts of the world. Looking at the tropics, we can see that the systems are actually moving from east to west most of the time, most of these locations. And we can see that the kind of structure of those systems looks quite different than it does in mid latitudes. Okay, so how are we supposed to go from these changes in global mean precipitation that connect to the global warming forcing and understand what's happening at these much smaller scales that are what we experience? Well, also, why should we do that? Other than because we want to know if we need an umbrella when we walk outside. Some people are motivated by money. So looking at this data from NOAA, the National Oceanic and Atmospheric Administration, list of disasters over the last 40 years that cost at least $1 billion. There's quite a number of them that have to do with either excessive amounts of precipitation or deficits of precipitation. So tropical cyclones are one, which of course have winds and a number of hazards associated with them, but one of those is heavy precipitation. Of course, drought and flooding are quite obvious here. And so these cost staggering amounts of money. So tropical cyclones on average over this period cost $27.3 billion each year. Droughts cost on average $6.8 billion each year, and floods $3.9 billion each year. These are in inflation adjusted terms. Just between 2010 and 2021, there have been $19 billion flood events that were driven by heavy precipitation. So that's one reason that some people care. If we look at the trends in observed precipitation over the US, this is the picture that we get. This is from the US National Climate Assessment, which last came out in 2017. We're working on the next version of this. However, at the moment, this is the most up-to-date version. And so you can see here, compared to the map of precipitation over the US that we looked at before, this one is quite a lot noisier. You can see these increases in the middle of the country, increases in the Northeast, decreases in the Southeast, and decreases in the Southwest. But we can see that there's a lot of local maxima and local minima, and it looks a little funny. Now, coming back to our picture of the Earth seen from space here. This satellite was launched in order to take repeat images of a kind of iconic image of Earth that was taken in 1972 by the crew of Apollo 17, one of these missions that went to space. And this became a very famous image called the blue marble that some people think is partially responsible for a lot of the environmental movements. It gives you a perspective of the Earth that we didn't ever have before this image was taken. And the way that I think this connects to our observed trends in precipitation over the US, what we've seen is that this observed trend is just from the one realization of climate that we experience on our one planet. And now this is a central challenge of climate science and for precipitation in particular. We only have one planet, so we only get to experience one realization of climate among the many that could happen, right? So climate is the study of kind of averages of what's happening with weather over very long time scales. So the more realizations of that we have, the more accurate estimates we can make. But we only have one planet. Now, you've probably heard of something called the butterfly effect. Now, the story that goes along with this is this notion that if a butterfly flaps its wings in the tropics, that could cause a tornado in Texas that wouldn't have otherwise happened. What this comes from mathematically is that you can have an infinitesimally small change or difference between two atmospheric states, and it grows exponentially very quickly, such that a couple weeks later, the weather will be completely different because of a change that's as small as a butterfly flapping its wings. Now, this is something that was revealed by Ed Lorenz with a series of computer model experiments, and it was illustrated very nicely with this simple three-dimensional model that has a lot of similarities to the atmosphere. But what this means for studying climate is that we always have to grapple with, were these trends that we saw things that were forced by climate change, or were they something that was just a random chance happening? And so because we only have the one planet to study, what we do is we build model simulations. We build models and we run them over and over and over so that we can simulate what would happen if we had many realizations of climate. So this particular climate model is built at NCAR. So I spent a lot of time working with people who build it, and there takes 100 or 200 people working on this project over the course of decades to have this very complex model. And there are about 40 of these around the world. So there are different modeling groups that build different models. They're all talking to each other, but they're doing their own thing a little separately also. And so that gives us a couple of different possible models of Earth that have some differences that hopefully give us a little bit of an idea of different ways that we can approximate what's happening on the real Earth. Okay, so these are really important tools for trying to understand precipitation and contextualize what it is that we observe in our one realization of climate that we experience. So some of the things we use these models to ask, some of the questions we use these models to ask are how did precipitation change in the past, and how could it have changed given the same forcings? How else could it have changed? And then we want to ask, how will it change in the future? Which has two different components. One component is, how is the global warming forcing going to change? And the other component is, what are the possible things that could mean for precipitation? How could that unfold? So if we compare 40 realizations of this same climate model for a 55-year period, so this is from 2005 to 2060, just a bit into the future, with the same forcing, these are the different realizations that we get. Now, there's nothing different about these simulations other than their initial state. Those differences are about the size of those butterflies flapping their wings. But we can still get many different outcomes. So this is just to give you an idea that this is a hard problem to try and wrap your head around. Here are, zooming in, 3 different of these model simulations. The average of all of the models is on top, and then the wettest and driest ensemble numbers are in the middle and on the bottom. And so you can see that this average of the model simulations is what we use as an approximation of what the forced precipitation response looks like. So you can see that there's, on average, an increase in precipitation toward the north and a decrease toward the south. But we can have many different manifestations of what that looks like when we add the forced change onto the different realizations of internal variability. Okay. I'll remind you that this is just when we're looking at average precipitation. So the hard problem, we have natural variability. We also, on top of that, have differences among climate models. So here are 40 different models, and it's hard to see here because they look similar overall to the magnitude of differences among the different realizations. However, these different models also predict slightly different changes in the forced response. Okay, so we want to know how much precipitation there is is hard, and also how it's going to change in the future. So let's see. Now, if we look at the simulated average precipitation change, the spatial pattern of this. So this is the spatial pattern of this global average increase in precipitation that comes from global warming. When we take along with the global mean precipitation change, and we also account for the changes in circulation and where different precipitating systems shift to on average of global warming, this is the picture that we get. So because there's an increase in global average precipitation does not mean that we have increases in precipitation everywhere on the Earth. We can see there are these large increases in the deep tropics associated with movements of that high region of average precipitation, the ITCZ. We can see that there are decreases over most of the most of the eastern ocean basins that extend over the continents over most continents. We can also see patterns in the zonal mean. If we average over all latitudes, you can see overall there's an increase in the deep tropics, and there are increases at the highest latitudes and decreases in precipitation in the subtropical regions. So there are some things that are consistent, even though on top of that, we know we have to think about this internal variability. So one of the reasons it's important to think about the variability is not just to confuse ourselves, but it's because we care about the variations over time in precipitation. So the variability of precipitation also, in a sense, leads to its extremes. So if you have average precipitation, that's always one magnitude, and you have larger variability, you'll end up with larger extremes. So if we compare the average precipitation change to the change in extreme precipitation, we can see some similarities and some differences. Overall, the spatial pattern is pretty similar. We can see the largest increases are in the deep tropics. We can see there are decreases in most of the Eastern Pacific Ocean basins outside of the deep tropics. We can see that the largest increases are at high latitudes of both hemispheres. However, on average, the extreme precipitation increase is larger than the average precipitation increase. This is something that's very consistent that we see among model simulations, and it's also something that has already been noted in observations. More regions have an increase in extreme precipitation than in average precipitation, and even regions that have a decrease in average precipitation, in many cases, see increases in extreme precipitation. Okay, so what can we do to try and understand this? So if we go back to the global mean precipitation change, this was documented back in 2006. If we look at these model projections, the increase in global mean precipitation is something like 1 to 3% per degree warming in response to a doubling of carbon dioxide. Now, we know that precipitation is a flux of moisture, of water vapor, right? So if we look at the water vapor on average, that actually goes up quite a bit more than precipitation in the global mean. And so one of the aspects of the response of the atmosphere to global warming, going beyond just the increase in temperature, is that we have this consistent increase in the amount of water vapor in response to warming. So the amount of water vapor that the atmosphere can kind of hold goes up on average by about 7% per degree warming. And the water vapor that we see in model projections and in trends and observations is very similar to this overall change. So what that's saying is that the changes in water vapor are kind of following the moisture holding capacity of the atmosphere. Now, if we think about a schematic of what happens when we have a system that results in precipitation, the simplest model looks something like this. We've got a concentration of water vapor in the bottom of the atmosphere near the surface. we've got vertical motion, vertical wind, that's just rising, forming a cloud, which then precipitates out all of that water. And the precipitation rate that we get in an individual event is pretty similar to the magnitude of this wind times the water vapor that's held in the boundary layer. And then if we think about a collection of these kinds of events all coming together, like this cloud scene I took a picture of some years ago in Colorado, we've got a distribution of different clouds, and we also end up with a distribution of different precipitating events. Each of these precipitating events, like these clouds, adds up to this total precipitation. So the total precipitation is kind of the sum of each of those individual events and how long they take, or the area that they cover. Big regions in between with no precipitation happening. So if we line up all of those different precipitation events and their different precipitation rates and accumulations, like this, we can connect up what's happening with the extreme precipitation events to the total precipitation, the global mean. So what this graph is showing is every precipitation event on the planet in a suite of many model simulations, with the most extreme events on the right. And they're just accumulating. So it's basically every event that's over each of these thresholds. So there's just a few events that are the most extreme. And then as we go to the left, we eventually get all of the precipitating events on the planet. And then this is actually a difference between model simulations about the present compared to the end of the 21st century. So this is looking at the change across these different degrees of extreme of precipitation events. And so what this shows is the connection between the increase in extreme precipitation events and the increase in global mean precipitation. These aren't two things happening in isolation. They're very much connected to each other. And so one of the things that I try to do, and that I think is one of the central challenges of understanding climate and how it changes, is understanding how and why this distribution of precipitation changes. What is this slope and why is it like that? Are the models capturing it accurately or not? How much uncertainty should there be? How much uncertainty is there? Looking at these pink and red lines over here, this gives us a measure of the uncertainty across the model simulations. And we can see that that's quite large when we're looking at the extreme precipitation. The model with the smallest increase is just above 5%, and the model with the largest increase in extreme precipitation is just above 15%. So it's quite a large range of uncertainty, and the models agree much more as we go to the average. Now, if we look at this in terms of the schematic of the absolute precipitation distributions, and we have moderately wet events to the left here and very heavy precipitation events at the right here. The current climate has this kind of peak at the more moderately wet events, and what we expect to see is larger increases in extreme events and actually decreases in these moderate events. This is another consistent finding that we see in climate model projections. So we expect that increase in precipitation on average to come unevenly in space and also in time, with fewer precipitating events overall, but heavier events when they occur. And this isn't something that's just been projected. As I mentioned, it's also something that we've seen in observations. So back in 2011, so over 10 years ago now, was this kind of first attribution statement that says human-induced increases in greenhouse gases have contributed to the observed intensification of heavy precipitation events found over approximately 2/3 of data-covered parts of the Northern Hemisphere land areas. Okay, so this is rather specific, Northern Hemisphere land, 2/3 of regions. However, nonetheless, it's consistent with what we see in model projections. It's not something that's particularly new at this point. Okay, so with that, I think that I'm going to, one more thing. So connecting that global mean precipitation to the extreme events is the variability of precipitation. In some kind of general sense, connecting that average precipitation to what's happening on the tails of the distribution is a lot more complicated for precipitation than it is for temperature. One of the things that I'm not going to go into in detail today, but I'll show you a cartoon of, is that we see in model projections that the variability of precipitation increases with global warming over time in future projections of warming. So that means that there are increases both in heavy precipitation events and also in precipitation deficits. So this is something that a bunch of people, not just me, have studied and call it things like precipitation whiplash, and it's something that we worry about for droughts as well as floods. Okay, so average precipitation is a hard problem, but one thing I haven't mentioned yet is the uncertainty about what we will do, what humans are going to do in the future, and that's also something that matters. So far I've mostly showed you simulations with just one kind of worst case scenario projection of emissions. This map is from, again, the National Climate Assessment from a few years ago now. We're in the process of updating. And it shows the projected change in daily 20-year extreme precipitation. So it's a measure of extreme precipitation with lower emissions on top and higher emissions on bottom. So the difference between the top and bottom rows here is what we do between now and the end, late century and mid-century. We can see that the increases are larger. The increases in extreme precipitation are larger in the case where we allow more emissions to occur. So this is yet another element that that introduces a lot of uncertainty, but also the reason I wanted to include it today is because it's wanted to make sure that you feel empowered, that there's not nothing you can do. There is something you can do. Okay, so global warming means increases in average precipitation in the global mean, but decreases in some regions. But that exact trajectory has a lot of uncertainty. Both because of the greenhouse gas forcing, also because of internal variability. And consistently, those extreme precipitation events increase faster than the mean. So that's all I have for you. And I will take the questions.
So please, the floor is open to questions, and those people on the webinar, please type your questions in Q&A, and I will get them to Angie.
So,
hi, thank you so much for coming here and presenting. So I've actually had personal experience with precipitation. I grew up in the Northwest, and so recently we've also had a lot of flooding and a lot of extreme rain. And so what do you think are some of the things that cities and governments may eventually be forced to take? Like, what are some of the drastic measures that they need to take?
yeah, okay, so I'm going to repeat the question for the people online. So I think the main question that you had is that what is it that cities and governments are going to have to do in response to these changes in extreme precipitation that we're already seeing. You've seen in Vancouver, I've seen in Seattle and in other places. I guess one of the main things I think that people are doing, water managers are already doing ahead of these kinds of changes is thinking about how they build infrastructure, right? So one point of discussion that people really want information about is when they're building a dam or when they're thinking about how to change a dam. So dams are used for a couple of different purposes. One is to provide water for people in times where there's not active precipitation. And another is to mitigate against floods. So if you have space in your reservoir, you can catch a lot of water before it goes downstream. And so one thing that governments are doing is thinking about climate projections when they're building this infrastructure. That's a very hard thing to do because this infrastructure sticks around for many, many decades. And trying to figure out what you need to do in order to plan for the next many decades is really difficult with all of these pieces of uncertainty. Another thing that I have heard more about more recently is thinking about stormwater systems. So in a lot of places, these heavy precipitation events can overwhelm stormwater systems and cause a lot of problems that way, and cause problems with water quality, also exacerbate flooding. And so planning that in as we try and update our stormwater systems is another thing that people try and take into account. One thing that I heard just happening a few months ago, but has been in the works for quite a long time, is planning for flood insurance. So homeowners, individual homeowners buy insurance so that when their house gets destroyed by a flood, for example, or otherwise is damaged, an insurance company kind of pools that risk from lots of different people and then helps them rebuild. So one thing that had been happening is that the national maps that estimated the flood risk in different places have become outdated as the amount of precipitation has increased. And so those estimates of flood risk have changed, have been updated. And the idea there is to get a more accurate, up-to-date estimate of how much risk different properties have, to try and figure out how much different people should be paying into an insurance program so that it's sustainable over time. In the past, there have been events that were very large and bankrupted insurance companies, which then caused the problem for the people who were expecting to be helped to get through those disasters. Those are three things that come to mind.
Where would you choose to live in the US if you want to avoid like extreme precipitation or other extreme weather events in like near like future?
Yeah, I think it's an interesting question, and I don't know that there's a great answer, right? So if we look at, so the question was, where would I live in the US if I wanted to avoid extreme precipitation events? So this is so if we think back to those maps of extreme precipitation, it increases in most places, but the impacts are very different depending on where you are. One thing that the last National Climate Assessment kind of emphasized was that there have been really big increases in extreme precipitation in the Northeast. Now, there's a lot of ongoing research into that, how much of that was forced versus how much of it was internal variability. And I think that a fair bit of it was probably internal variability. I think that we'll see increases that are larger in other regions and less large increases in the Northeast on average in the future. So I don't think that there's a particular place where you can really escape extreme precipitation events. But if you think about what they mean, what their impacts are, there can be really dramatic differences. So thinking about the Pacific Northwest, one of the challenges there is that already at present, the seasonal cycle of precipitation varies a lot over the US. And so the summers are very dry in the Pacific Northwest. And when you get to the end of the summer, the water is basically coming from melted snowpack. So there you have some, you won't necessarily have water at the end of the summer if you have precipitation deficits. Further south in California, you get something similar, only there's also kind of less precipitation on average. So California is a place I would not go, but not because of the extreme heavy events, because of the extreme lack of precipitation. I think that the thing is, there's not really, that it's not that easy to escape these things, right? I don't have a great answer. Kind of depressing, isn't it?
Okay, so there are a couple of severe drought events due to climate change. And how do these severe droughts account for the increasing amount of precipitation and increasing amount of extreme rainfall? I mean, like if the area has experienced severe drought, does that mean like the other area have more rainfall to like outside the droughts? Is there any relation to that?
So some of it, yeah, so this is a good question. So there's like a lot going on, and how do you have increases in drought? How do you have increases in precipitation deficit when precipitation is on average going up over time? So it kind of comes back to this increase in variability of precipitation. There's also another factor. So when we have precipitating events, they're heavier on average with warming, and then it's raining for less of the time overall. So the increase in precipitation is coming during heavy events, then moderate events become less frequent. Okay, so that's one component of it. And then the other component is a drought also is depending on the sequencing of precipitation. There's a third factor, and the third factor is the increase in evaporation and kind of evaporative demand in the atmosphere. So one component of drought is the amount of precipitation and its sequencing. But when we're really thinking about drought, it's something that's happening on the surface. So you can make it drier by putting in less precipitation or by pulling more water out of the surface. And in response to warming, that increase in the thirst of the atmosphere is also a driver of drought. Drought's also pretty complicated, right? There's a lot going on, and a lot of times it's unfolding on a slower time scale than when we're thinking about extreme precipitation events. So just like with these other precipitation events, the internal variability is a large component of what's going on. So that's complicated and circular answer, but hopefully gives you a little bit of an idea.
So here's a question from the webinar.
Mm-hmm.
And the question is, what's the most surprising interaction you've seen between the microscopic and macroscopic aspects of the water cycle?
Oh. Let's see. I mean, I think that the thing that surprised me most probably was right at the beginning of my work. Maybe I don't know how much it counts, but I think it's a really interesting one. So when you have a tropical cyclone, the tropical cyclone, we think about them being these kind of organized systems where there's wind that's swirling, but actually this swirling wind is the energy that drives it is coming from that condensational heat. So the structure and the orientation of things like the eye wall and the latent heating coming from the eye wall, whether it's straight up or more slanted or even more slanted. These are kind of, maybe not a microscopic scale, but it's pretty small scale, small differences end up having a big impact on things like the intensity of a hurricane, how fast the winds are and how low the pressure gets.
Thank you.
So with these heavier events, precipitation, how do you see the role like runoff and soil erosion being affected by this? Like coming from an agricultural perspective, like if there's like, soil erosion is a big problem with like agriculture. So how do you see that playing?
Okay, so I think the question was, how do I see these changes in precipitation affecting agriculture? Yeah, so definitely one thing that has happened in the last few years is that farmers weren't able to plant their crops because there were floods. Another thing is that we know that most crop yield are very sensitive to precipitation. sensitive to temperature, but they're also sensitive to precipitation. And so people worry about changes in crop yields because of warming, but the changes in precipitation, it's timing, how heavy it is, and precipitation deficits all matter a lot for agriculture. And so this is a really hot topic in the literature. It's like very active thing that's going on. And so I wrote a commentary a few months ago that ended up being quite complicated, where it's not actually just the precipitation that matters, but the coupling between the temperature and the precipitation and how that can change in response to warming can be just as important for the warming response alone as the warming response alone to agriculture. So I think it's complicated, and it's something that I'm going to be looking at. I have some funding to be looking at, but there's not an easy answer, I think.
How will an increase in precipitation affect the seasonal snowpack in places with very cold winters?
Yeah, so the question is, how will precipitation change impact snowpack in places with very cold winters? Yeah, okay.
Yeah, and like, how would that affect like, water supply?
Yeah, so also how would that affect water supply? So one of the things that's, I think, pretty straightforward to understand about global warming is that as it gets warmer, we expect to see more precipitation falling as rain that would have fallen as snow in the past. So that's a kind of average warming effect. It's just less snow falling, more falling as rain. And so that overall would cause a decrease in snowpack. And that's something that people worry about a lot, especially in these regions where a lot of the water supply, especially in the summer, is driven by this snow melt filling reservoirs. And so that's something that's a big concern.
I just want to ask from a scientific standpoint, is the biggest solution to this decreasing warming, or are there any other mitigants that decrease like extreme?
Yeah, well, I mean, since a lot of the precipitation, especially the extreme precipitation event, is coming from the increase in water vapor, which is pretty closely tied to temperature, then decreasing the warming and decreasing global warming forcing is really the way to get at that. One thing that is a little bit perhaps counterintuitive. So one thing that's been discussed a lot lately are these different approaches to geoengineering, right? Where we try different approaches to getting rid of some of the radiative forcing by methods other than just decreasing greenhouse gas emissions. One of these is stratospheric sulfate aerosol injection, so kind of emulating volcanic eruptions. And so thinking back to the diagrams of the energy balance in the atmosphere, those decrease warming, not by changing the emission from the Earth, but instead by decreasing the absorbed solar radiation. So you're tweaking a different knob than you were tweaking with the original greenhouse gas forcing. Because precipitation is affected a little bit differently than temperature, right? So we're worried about the surface and top of the atmosphere instead of just the top of the atmosphere. The effects on precipitation are a little bit different. So if you cancel out the greenhouse gas forcing exactly by reflecting more sunlight back to space, by changing the planetary albedo, you actually decrease the total amount of precipitation. So you can get rid of the warming, but then you do something else to precipitation. So it becomes quite complicated to deal simultaneously with the changes in temperature from greenhouse gas forcing and also the changes in precipitation.
So for the projected change in extreme precipitation model that you had, you mentioned both lower emissions and higher emissions. But I see that even for the lower emissions, that there's still going to be an increase in extreme precipitation events.
Yeah.
Is there a way to, I guess, like potentially mitigate that so that we're at actually like no change instead, or is increase in precipitation inevitable?
I mean, at this point, right, 2022, we've been emitting greenhouse gases for many decades, a couple of centuries, with increasing rate. And so quite a lot of that warming and thus quite a lot of that extreme precipitation increase is pretty much baked in at this point. So yeah, there's not really a way around that.
I have one question for you.
Yeah.
So it looks like from the projections, what we want to know is how precipitation will change locally.
Yeah,
And that's so the farmers here want to know.
yeah.
So it looks like precipitation will increase in New York. Because the question is, how confident are you in that? And then how confident are you with projections locally of changes in the variability of precipitation? Because I guess that will also change locally.
Yeah.
Some places might see great variability, some places might not be.
Yeah.
So how confident can we be in local projections?
Yeah, so I think that this is one of the hardest problems. So when we're thinking about global averages, we can make really confident statements because we're averaging over huge spatial areas and also over long time periods potentially. So we can make pretty confident statements. And that's why climate scientists do that. But when we get to the scale of an individual farmer wanting to make decisions about their individual farm, we have to worry about all of these natural variability aspects coming into play. And so people want to know what's actually going to happen. And I think one of the hardest things about climate science is to convey this uncertainty that's huge in the difference between the force response that we expect. So I can very confidently say that the force increase in extreme precipitation will be positive. I can very confidently say that on average, the variability will go up, that a little bit less confidently on the local scale than I would say for extreme precipitation, depending on exactly what aspect of variability we're talking about. But that's quite different than making a statement about what's definitely going to happen over the next 100 years. There are a lot of places that are going to see increases in extreme precipitation and also in variability, more places than will see decreases, but also a lot of places will see decreases, not because it's not forced by global warming, but because there's this huge element of weather. So trying to quantify all of that uncertainty in a way that is useful and allows people to kind of make decisions, knowing that a whole bunch of them are going to 100 years from now look back and say, we actually saw a decrease in precipitation or a decrease in extreme precipitation. And that separating out that part that's forced by climate change versus the part that was just natural variability that I knew all along was going to happen is really hard to do. So one of the things that all of you should do going forward in whatever it is you find yourself doing is try and understand and wrap your head around this massive amount of uncertainty that's alongside information that we're very confident about. A lot of things, climate being one of them, are really complicated to try and wrap your head around. It's not as simple as this thing happened and it's because of this thing. So it's a lot more convoluted than that.
Thank you. I would thank Angie Pendergrass again.